I asked Don Stoner to come and finish this up, and I think you'll find very much food for thought, many good details in Don's stuff, and I want to welcome Don again to speak again.
Let's see, what am I talking about? Oh, external context for Genesis chapter 1. Now, how old is the earth? We've got a couple positions here. There doesn't seem to be anyone that takes an in-between, 4.5 million years old. It's always one or the other. Just out of morbid curiosity, would you be too embarrassed to vote on this? You know, how many think it's number one, 4.5 billion years for the earth? And well, that's the universe, not the Earth. 13.7 is the actual number from the satellite. Now, who thinks it's, what did I say? At 10,000 years, that could be 6,000, or I think Gerald Ardsma at the ICR says 30,000 years. Have we got anyone here that believes it's that? Nobody that's willing to admit it? Is that what it is? Or okay, probably it's mostly an old Earth crowd here. Usually I get a split. Sometimes it's 90% young Earth. If I'm doing an 8-week session, it starts out 80-90% young Earth at the beginning, and they're staring around thinking, those are my friends that are putting their hands up for old Earth. They're absolutely shocked. By the end, it's about 95 old Earth and 5% young Earth, and that 5% is usually one hand. How old is old? Well, I'm breaking the line somewhere between those two, and there's a dead area in between. So let's go for the next slide here. Now, you'll notice that if you divide 4.5 billion years by 10,000 years, the factor is 450,000. Now, that's a fairly large ratio. That's the equivalent difference between 7 miles and 1 inch. Okay, next slide here. We got a map of Beaver Creek or wherever we are in Dayton there. That's 7 miles between those two. Now, we could get in an argument with someone. Are we talking about 7 miles between Beaver Creek and Dayton? Or is it 1 inch? And you can imagine people getting hot and presenting arguments both ways. Well, actually, you can't. It seems like it ought to be pretty obvious. Now, we have different presuppositions, and maybe our presuppositions will force us to see an inch, or maybe they'll force us to see 7 miles, or maybe this whole idea is really bogus, and the evidence is really going to overweigh any presuppositions we might have if we really are keeping our eyes open. I'm going to concentrate on the scientific evidence first. Okay, next slide here. The Bible says, Psalms 19:1 and 2, I've already quoted this and you're all familiar with it. The universe speaks truth. Next slide. Get the same thing in Romans 20. You can see God's invisible attributes, His eternal power. Are we supposed to see somehow a reflection of God's eternal power in the universe? Romans says we are. Next slide. Some attributes of God here. We got natural attributes. He's eternal. Moral attributes. He's truthful. Next slide. He doesn't lie. He doesn't change. We're not expecting the creation to lie. We're expecting it to tell the truth. Next slide. Now, if we make an argument, it's like a chain. There are a lot of steps in it. And if one step goes faulty, the chain breaks. The argument's no good. You have to get every single thing. You got to get all your ducks lined up. There's the proverbial weakest link in the chain you keep hearing about in the metaphors. Next slide here. Okay, the first link. It's important to understand the argument. If somebody gives you an argument and it's about nuclear physics and it proves the Earth is young or it proves it's old, it doesn't do any good, does it? Unless you happen to have a degree in nuclear physics. Okay, we've got a young man there in the background of the depiction of the stoning of Stephen by an artist some time back. He seems to be wearing purple and green or something. He has some advice for us. He says, zeal without knowledge is not good. He's exercising some zeal there, but he's missing some important data. And his advice to us later in Romans 10:2 is don't do it that way. Make sure you know what you're doing. Next slide. Okay. Seasons are pretty well understood. Down in Southern California, we don't have them, but most of the rest of the country does. Most of the rest of the world. We got a tree here that does different things different times a year. And next slide. There's a reason for that, and that's because of the astronomical geometry of the Earth and the Sun. It kind of makes a seasonal clock that makes ticks on that tree there as it's growing. You can see summer and winter rings. Next slide, please. And this piece of wood is kind of like a running tape recorder. we can tell which years, starting from the present. I need to get the pointer again, don't I? Thank you. Starting at the bark, this is the present. If you just cut the tree down and it's new, and this would be 1 year, 2 years, like that, you can tell this was kind of a bad time to be a tree. You didn't grow very well, but over here, man, everything was going right for you. It tells you everything about the whole time that this tree was alive. It's not just when you cut a tree down, it doesn't just tell you how old it is. It tells you lots of stuff. Okay, next slide, please. In fact, this tree here records a series of forest fires that you can see, which years were very, very bad luck for trees. Next one. Now, if you want to know how old a tree is, let's go over the links in the chain that's required. You count the rings, 1, 2, 3, and you get 50 from here to here. Next slide. Okay, that's the distance. How far have we gone here? The equation is distance equals rate times time. You get that in physics all the time. In this case, the distance is equal to the rate the distance 50 rings is equal to the rate that rings grow. It might be 2 rings a year, 1 ring a year, times the amount of time. If it's 1 ring a year, that would be 50 years if it's 50 rings. That's the equation. We're looking for weak links in our chain here. Next slide. Okay, is it really equal, for example? If there are miracles going on, maybe God created that tree with all the rings in it already, then we don't know anything. That's a broken link in the chain. Next slide. The rate. How many rings a year does it add? Well, there's a reason why it should be 1 a year, and that's because we have this clock driving the seasons, and that's why trees are thought of as growing 1 ring a year. Next slide. However, there are situations where you get trees that don't grow 1 ring a year. There's some places where they have 3 growing seasons because of parasites, where the tree starts to grow and the bugs eat off all the leaves. They try again, they can get 3 rings a year. At the Institute for Creation Research, they took some bristlecone pine trees and tortured the poor little things to produce 3 rings a year. You can do it. Okay, 1 ring in 5 years is a possibility, maybe 5 rings in 1 year. There are things you can do to a tree to make it produce an anomalous number of rings. So we might say instead of 50 years, this tree could be from 10 to 250 years old, and it would fit in the range of at least plausibility, if not probability. However, if we take the same ratio that we're looking for in the age of the Earth, that's like claiming maybe it's 10 days old for that tree. Anyone buy that? Or 10,000 years old. Anyone buy that? The number's too big here. At least for tree growth, it's not going to work. Next slide, please. Okay. Could we challenge the mathematics? Yeah, when you multiply that by that, do you really get the product? Or is the idea of distance equal rate times time a bogus idea? And we're really not being productive challenging this. I think we're going to let math slide here and say that that's a good link. Next slide, please. So, if we've got all of these things lined up, we know some slop on our rate here. We at least can get t within some margin of error. If we know this, we've got that. The chain's done. There's nothing to argue about. If we don't know one of these, then we can argue about t. Next slide, please. Okay, trees are all too young. The oldest trees living are just under 5,000 years old. And when they look for dead wood on the ground and line it up because they can see ring patterns matching, they get back to a little over 10,000 years. But you can't go back far enough to make the decision with trees. So we'll go to the next slide. It turns out there are other things in God's creation that have tape recorders running. This is a lake seen at different times of the year. I've got 3 different times here. And the crud that piles up on the bottom of the lake, you can see some moss in the water there. There's a lot of calcium carbonate in the water during spring runoff. So in spring you get a calcium carbonate layer. Later in the summer you'll get kind of a mossy layer. And it piles up just like tree rings in the bottom of the lake. Next slide, please. You've probably all heard of the Green River Formation. It's no water. There's no water up there either, is there? Could somebody run and find some for me, please? Otherwise, I'll die up here. Thank you. Okay, the Green River Formation covers... Oh, thank you, sir. Take back all the evil things I said about you. Okay, the Green River Formation, this happens to be in Wyoming here, the Fossil Butte National Monument. It also covers a lot of Utah and some of California. Next slide. It has a layer, it has a stack of layers. It's about a mile deep. for the whole formation. In some places, they're thick and thin places. That's my daughter pointing to the layers for you. It's got the same deal. It's a tape recorder. You can see everything that's going on. Next slide here, and it's also got a bunch of beautiful fossils in it. You see these fossils all over the place, and they're an interesting question all by themselves. How did they get there? And I'll cheat and tell you the answer. Every now and then, the river that was feeding this lake cut through a salt formation, killed everything in the lake at once. Not only killed the fish, it killed the crocodiles that would have been eating them, the germs that would have been eating them up, so these fish are preserved. They're all salted. And so every now and then, you get really beautiful fossils. It only happened a couple times during the whole lake's history. The rest of the time, everything rotted when it got to the bottom except for clams. Okay, next slide, please. I told you the formation was big. It's 10,000 square miles, and this is a rectangle of about 10,000 square miles. And you can see the formation. This thing here is where the surface is cut through, and you're actually looking at the edge of the formation. Next slide, please. It's a mountain range today. This lake bottom got eroded, or first it dried out into shale, hard rock, some limestone, and then it eroded away into all these peaks and mountains with valleys in between. Next slide, please. Okay, when you try to find the place here, it's 191 between Duchesne, and this would be Helper and Price down here. So if you're cutting across the states in 40 and headed down 191 and you stop, it's right at the south edge of the Ashley National Forest right there. You can see the formation for yourself. 73 Volkswagen is overkill for your scientific equipment. You can get a hold of the Roadside Geology of Utah, or a geological map, which we got shown earlier today, and it shows you right where it is. Next slide. And this is what it looks like. That sign says you are now leaving the Ashley National Forest or something like that. And these are all the layers. And when it erodes, it leaves this garbage beside the road that you can pick up and play with. It's like potato chips. These layers break off into thin little slices. Next slide, please. And you can measure them. There's one between a dial caliper that's reading 40 thousandths of an inch. There was a younger man picking them up and measuring them in the headlights of a Jeep one night. What's the rate? How fast is this laid down? Well, it's a question. The standard answer is that it's one layer a year, one pair a year, because that's what the clock's driving it. But some people would challenge it. Maybe it's one layer per every storm. You get runoff that sets a layer. It's an honest question. Next slide, please. And the distance, well, the way you figure that out is you notice the thing slopes. There you can see it heading down the road cut going down the mountainside. You can measure it just, counting the layers could take a while. But anyway, you can see how you can get the full thickness of the thing without doing a drill core. Your 73 Volkswagen, or in this case, somebody's camper, is enough to take you the whole length of the whole mile thickness of the thing there. Okay, next slide. And a little bit of mathematics. You drive 3 miles. If you got the right angle there, you get a mile of thickness. You know how thick these are by measuring a few 100,000 of them or something. And by doing the math, by my measurements, I get at this location probably 1.5 million layers at this spot. Now, that there are different parts of the formation that have more and less layers. There are estimates that there are 4 million layers in the entire formation. Now, how did they get that? Well, same way I did, but different places, and did it more carefully than I did. I was passing through there pretty quickly. There are different numbers published for this. I'm using 4 million because that's the smallest estimate I've ever seen in print. Most people say 5. You can get up to 10 million layers from estimates. I'm trying to give the young earthers the benefit of the doubt here. We've got to deal with 4 million layers, okay? Or we could cut back to 1.5 million if we just want to go with my number. Next, please. Standard interpretation, 4 million years total, if we've got all these things lined up. But how strong are the links? We've got to test them. Next slide, please. The distance. Is it 4 million? Well, I'm trying to be conservative. You could maybe argue me down to 1.5 million, but I've counted that many myself, so I can't go much lower than that. Next slide, please. So the young earthers, what about the rate? The young earthers will say, well, let's look at Lake Walensee in Switzerland. Here's a lake that there was a canal put in, and they go through this whole thing, and it says, look, it's 2.5 layers per year. See, your varves aren't actually years, because this particular lake, because of silly things that are going on, actually produces 2.5 layers per year. What if we say 5-layer pairs per year for a peak rate? Well, that's their peak rate. They've caught it doing 5 layers in 1 year. What if we say 5 layers every year or something like that? What will that buy us? Next slide, please. I'm going to say 1 layer every single day. I'll go along with this. Okay, next slide, please. 10,950 years, and this all has to be laid down during Noah's flood, right? What would it take to get it during Noah's flood? What would we have to do? Next slide, please. Well, you do the math backwards. It takes 8 seconds to put down a layer. Now, next slide. Let's go back and look at this again. What can we do to something that's 100 miles by 100 miles that'll change the entire composition from this entire area of turbulent floodwater from rich in calcium carbonate to rich in organic matter and back again every 8 seconds? Okay, this is a hard one. Next slide, please. I tried to pick, this works down home where I live. You can look at that and see what it looks like at your hometown. I don't happen to have it for everybody here, so you'll have to put up with Los Angeles. There's Los Angeles, there's San Diego. That's the size of the formation. Oh, I'm sorry, San Diego, Los Angeles. Next slide, please. Here's the way to do it. We could have a wave go by. This would be like paint rollers. There are young earthers who claim something like this is what's going on. Each wave carries sediments along, and it's depositing one kind here and another kind here. They've got one guy who mixes up different kinds of trash that have dark and light stuff in it that settles out fast and slow, and puts waves in the water, and they can put layers down fairly quickly. Now, so far he hasn't managed to do one every 8 seconds, but it's an interesting idea anyway. So each wave has to carry 1/30 of a cubic mile of sediment for 100 miles. It's starting to sound a little suspicious here. 50 feet is as large a wave as we can get that repeats every 8 seconds. You make them bigger than that, it takes too long for the waves to go by. You can get them, if you have little waves, you can get ripples to go by faster than one every 8 seconds. But if we're going to do it one every 8 seconds, we've got to have 50 feet or smaller. Now, a 50-foot wave's pretty big. Next slide, please. Here's a big wave. There's some people standing on the beach there, and there's this wave breaking out here, and we'll watch this wave come in. Next slide. Here it is a little bit closer, and it looks pretty big. Next slide. There's somebody there thinking maybe they've made a mistake. Here's the wave coming in. Next slide. And here's the photographer, and this is the last picture he manages to squeeze off before he and 100,000 other people got killed in the tsunami. Now, if you look closely, this wave is not depositing dirt, it's picking it up. And there's a good reason for that. Next slide, please. If it travels fast enough to overtake a man running for his life, it will pick up dirt. How still would the water have to be to deposit 5 grains silt? According to the textbooks, 0.45 miles per hour or less. If it's faster than that, that's a fourth of the speed of a slow walk there, it's not going to deposit anything. Next slide, please. So we can do an experiment. You can pick this stuff up, you can grind it up with a mortar and pestle and stir it up in a beaker, get a timer. Next slide. Now this is Green River Formation shale. Here you start, you mix it all up, very fine grain. It's the same stuff that we're going to have to deposit. 6 seconds later, 18 seconds later, 30 seconds, I can almost say 37 seconds. Minute and a half, 6.5 minutes. You can see it kind of sort. This is absolutely still. 10 minutes, 24 minutes, 36 minutes. Well, we're starting to get a layer. It doesn't happen once every 8 seconds. There is no way you can do it. Next slide, please. The Noah's flood rate is a broken link. You can't get those layers down that fast. It just won't happen. Next slide, please. The Green River Formation was not laid down during Noah's flood. Well, let's try something else. Next slide. Possibility. We'll give it 11,000 years. That was the number we got if we give it 1 layer every single day. I was being generous, but let's do it. 1 layer a day, 10,950 years. We get our 4 million layers there. Business as usual, no miracles. We can assume miracles later, but not yet. What about the rate? Next slide. Okay. I'm going to see if I can figure out how to get 10,000 layers there. Actually, there's another problem we're going to look at first. This is the Mississippi River, and this is the Colorado River. There's some people riding in that mess. A little cleaner here. But together, these two rivers transport 1/10 of a cubic mile every year. Okay, next slide. That's Colorado and Mississippi.
A total or each?
That's the total of the two combined. Together they drain 2/3 of the area of the continental United States. Never mind Alaska and Hawaii. I'm not going to count those. If we could reroute those two rivers so they both puddled up into one lake here, and we put every little bit of sediment that ever went down those rivers into that lake, and nothing ever poured out of it, we get nothing but pure distilled water coming out. And of course, those rates are modern rates. Before farming showed up all over the United States, the rivers were a little cleaner. So we're being generous, and we'll just let everything pile up in that single lake, and somehow we'll figure out how to do 1 layer a day. It doesn't matter how. Next slide. 1/10 of a cubic mile per year. The whole formation, the lake was 10,000 cubic miles. It would take 100,000 years to do the lake using natural methods. Well, these aren't real natural, but we're trying to bend things as far as we can. Doesn't work that way either. Okay, next slide. There's two ways that we can't do it. We can't do it during Noah's flood, and we can't do it in less than 100,000 years, disallowing for Noah's flood. Okay, next slide. And this whole formation sits up here. Here's the Grand Canyon, the Grand Staircase, and all of this, that's a mile thick there, and we got a couple miles here. That had to go down before the Green River Formation strata was laid down. So the red wall limestone, that's the pink layer there, and everything else had to add to our number. Next slide, please. And we need to dry the lake up and weather it into a mountain range when we're done. This is all stuff that we've got to take care of if we're going to explain this anyway except as an ancient formation. Next slide. So we're kind of stuck with, let's see, what have we got? We've got distance, we've got rate. Serves no useful purpose to distrust logic or mathematics. Boy, we only got one more chance here, don't we? Let's try that. Next one. What? Are we dealing with a miracle? What if God created the whole thing in situ, right? Next slide. Well, we got two things. But first, if it's a miracle, then none of this matters. It doesn't matter how thick the layers are. It doesn't matter how fast we can put them down. It doesn't matter anything. It'll just happen. Next slide, please. However, there's two parts to the debate. There's science and the Bible. Science being the study of the creation, theology being the study of the Bible, and usually I've given a talk where I explain this first. But anyway, we've got to worry about the biblical half of the argument too. Next slide, please. Since the creation of the world, God's invisible qualities, the eternal power and divine nature, have been clearly seen, being understood from what has been made. So when we look at this, we're clearly understanding what's going on if this is telling us the truth. And we can see God's nature from this. Now, liar is not one of God's physical attributes. Falsifier, equivocator, prevaricator, dissimulator, those are not, that's not what God is. We're supposed to see His eternal power in this other than, not something else. Next slide, please. Okay, let me back up again. Can you give me a back arrow on that one? See if it works. Okay. We've got 1, 2, 3, 4. We've got the time nailed at this point. We know there can be no argument anywhere that says otherwise, and this lake took a long time to put down. It did not happen in 10,000 years. Okay, now next slide. So given that the young earthers know that there are arguments that prove this, what would they say? Well, here's an argument. The creation model permits us to look seriously at those natural processes which seem to favor a young earth and a recent creation. We shall see later in this chapter that there exist many such processes. Unfortunately, most people do not know this, since we were all indoctrinated as children in school with one model of origins exclusively. Next slide. Okay, this is a quote from Scientific Creationism. Henry Morris edited this book. There's the information on it, including the page numbers you get the quote off of. He's telling us that the universe is schizophrenic, that sometimes it tells us the Earth is old and sometimes it tells us the Earth is young. And he will then argue that there are probably more young Earth arguments than there are old Earth arguments, so never mind if I've actually proved it's old, because he can come up with 1,000 arguments why it's young. Okay, next slide. Okay, and I'm saying that I doubt it based on this verse here. Okay, next slide. The only possible way to get an argument that would say something different than what a good argument would prove would be to come up with a bad argument. We would have to use faulty logic. Next slide. So, I'm going to make this as easy as possible. I'm not going to say you guys have to come up with more arguments for young Earthism than I can come up with arguments for old Earthism. I'm going to only put up one argument. Now, I can do millions of arguments for an old Earth. One's good enough if it's a good argument. And my challenge is that the universe will be consistent, and if the Earth is young, if it's old, there will be no valid proofs that it's young. All you have to do is show me one good argument, and I'm finished. I'll say I'm wrong. But it takes one good argument. Now, can we do that? Next slide, please. Here's some of the guys that present you probably know this, that fellow there at least, and that would be Walter Brown, Wysong, Dr. Wysong, Henry Morris. I've debated this guy, Russ Humphreys, a few times. Josh McDowell actually was in this many years back. Ken Ham, of course. Dr. Dino, can't remember his name right now. Hovind, yeah. Presently operating out of South Carolina. Walter Brown put up a lot of arguments. I picked these guys because they tend to be fairly big names. They do a good job footnoting their arguments. Okay, next slide. And what I've done here is collected some of the more common arguments, and then which one of these guys, 1 through 7, present that as a good argument as of the last I heard from them anyway. So this would be probably a good young Earth argument. This would probably be a good one here. Some of these are fairly new arguments. The problem is these old ones get shot down by nasty people, so they have to keep coming up with new arguments. So Russ Humphreys is kind of cutting edge stuff here. These are mostly from a book called Rate 2, Existence of Polonium Halos. Josh McDowell picked up early on, but it's becoming more and more popular because not too many people have refuted it. So what I've done here is, well, I've refuted all of them, of course, but I've picked PowerPoint sections to show you how to refute some of these. Now, I'd like to get you involved. Would anyone like to pick a favorite argument? What have you seen at the Creation Museum or something you think you'd like to see the answer to? Next slide. These are scriptural arguments that supposedly prove that the Earth is young too. I won't concentrate on these. I'm a scientist, so it's a little out of my field, but I know the answers to them anyway. Death preceding the fall, I've dealt with that. Examples of the word creation used in the New Testament. Does it really refer to the creation? I've dealt with that. Okay, back up to the other argument. Does anyone want to pick a favorite here?
That the continents should have eroded away.
Okay, I like that one. Continents should have eroded away. The argument's easy to understand. You've got these rivers, the Mississippi and Colorado rivers, taking away 1/10 of a cubic mile a year. How many cubic miles are the whole continental mass? And you do the math, and it's not 4.5 billion years. It's much shorter than that, right? You do the math, you find out it is. And, of course, we've got rivers all over the world, so why are there any continents left, right? Okay, I could go there and show you, or I could just show you the argument right under it, which I have a ditto. Too much lava buildup. Volcanoes erupt. You know where this is going, don't you? Remember that book, Scientific Creationism by Henry Morris? He's got both arguments. They're 1 page apart. He does the math both times. He gives it to you in different units. But if you do the math, you'll find out it's the same rate. The volcanoes are adding lava, which turns into soil and gets eroded away, and they balance. Solomon says, the water flows to the sea, but the sea is never full. Two good young earth arguments, right? because the second one is from where the waters go, they return to their source, and we could argue half of the argument either time. Okay, it's half of an argument, and they make both of them. There's people supporting this argument, and here's people supporting this argument. They cancel. They cancel exactly.
So does that mean that all the dirt we have, it is replaced by volcanoes?
There is something, you've heard of the water cycle. There's also a rock cycle. And it's all been tracked out. You can track how much of it goes where and at what rate. It turns out Dr. Austin has written stuff on both sides of the equation there. He wrote under a pseudonym Stuart Nivens when he was trying to get his PhD, because everyone that went to study geology at the time that said they were a creationist became an evolutionist before they got out of college. So he kept his light under a bushel so he could actually get a PhD in geology. Anyway, that's how those two showed up. Anyone want to pick another favorite argument?
How about the existence of polystrate fossils?
Polystrate fossils. Well, I got a picture of one of them. And bang, there's a polystrate fossil. This happens to be in the Green River Formation. Okay, we got layers here. Here's this perfect looking leaf. 1, 2, 3, 4, 5, maybe 10 years. I didn't really count those. And all of a sudden it bends over at 90 degrees and it's rotted. What happened? We lost the salt in our lake. It's no longer preserved, right? You've heard trees going through coal seams and things like that. What do they say at the ICR? A flood did it, right? Do evolutionists believe in floods? Yes, they do. If it works for the ICR, it works for the evolutionists too, right? An evolutionist can say a flood did that, if it takes a flood to explain it, or they can say something else, like that there was salt in the water. There are all kinds of arguments that explain polystrate fossils, and any argument that works for a young earther also works for an old earther in this context. So we have an advantage here. I don't even have to answer them all. All I have to say is a flood did it, and I've done as good an answer. Now, it turns out in every case I can give you a better answer than that. Sometimes it really is a flood, but sometimes it's something else. C14 and coal, very interesting one. That's in rate 2. As I said, the other ones have been shot down. We've got to come up with new. Okay, here's the paper from rate 2, measuring C14, fossilized organic material, coal in this case. And somewhere down here, oh, there's his name, Geem. You can almost read this. The print's kind of fine. Next slide, please. Specifically, Dr. Paul Geem. He teaches out in my neighborhood. He's a friend of mine. That's a grand mustache he's got. He shows contamination of the C14-bearing fossil material in situ is unlikely, but theoretically possible and is a testable hypothesis. There's an interesting discussion I had with Dr. Geem. I advertised for the 10 best young earth arguments, and he showed up at one of my Mars Hill Club meetings to discuss it. He brought the thing in, and we discussed it. Where does the coal go through? Let me go through the argument. We've got coal. Coal's very old. Half-life of carbon-14 is like 5,770 years. All the carbon-14's essentially gone in maybe 5 or 10 half-lives. So how come there's a tiny little bit of carbon-14 left in this coal? Well, do you know how carbon-14 gets in the atmosphere to begin with, anyone? I'm a physicist. Oh, we got a physicist there. Okay. Nitrogen-14 in the upper atmosphere gets hit by solar radiation and it turns it into carbon-14. Neutron radiation, right?
And that can happen anywhere.
It's true. It can happen down in a coal seam, too. If you've got nitrogen down there, or if you've got carbon-13 or other isotopes, like down in a coal seam, a little bit, not much, is going to get turned back into carbon-14 again. I pointed this out to Dr. Geem, and he said, oh, we need to do some more research. Or stated another way, contamination is possible, but unlikely, theoretically possible. It's a testable hypothesis. I said, go test it. He got back to me later and said, well, we're on the edge of proving this. I said, good, call me again when you get it. That was the last communication. Okay, it's a good argument. I thought it was very interesting. And actually, I'm rooting for him. If he can prove it, that'll be really interesting.
So the coal is getting carbon-14 contaminated while it's under the ground.
It's getting it.
From the neutrinos.
Yeah. neutrinos and other things. Part of it's contamination. Water comes through with nitrogen. There is radiation in the coal near it, U-238 and stuff like that, that's bombarding it with neutron
Solar
radiation.
Caused by neutrinos, solar radiation. Neutrinos just go straight through the planet, usually not noticing.
Yeah, we get neutrons down there straight from radioactive elements like potassium and uranium that's in the rock too. It does produce it at a finite rate, which is why there's a little bit in there. And it's also why the scientists will say, you can't date stuff that old. The thing won't tell you anything because they know if the contamination is going to swamp your number. It's not because they refuse to accept the evidence. It's because they know good and well that the evidence doesn't mean anything. The contamination levels are too high. Pick another one. Moon dust. Is that on here somewhere? No meters, not interior. Moon too cold. You like that? Moon too hot. Moon too cold. Up the top here, not enough cosmic. This is one of the early ones. Why are there such shallow footprints? Hans Peterson made an estimate back in 1959, 2 years after Sputnik. How do you get the data? We didn't have much in the air making measurements. That the rate of stuff falling in, the meteoritic dust, would make a big, thick, 100-foot thick layer on the moon. And when we get to the moon, these astronauts' footprints are half an inch deep. Next slide, please. Interesting question. Wait a second. Half an inch deep footprints, but how deep is that dust? That's a lunar rover. That's the Lunar Grand Prix, actually. They're testing the thing out to see what it'll do. That's my daughter again, standing on the beach. And you'll notice that even though the footprints here from people walking are very shallow, the sand goes down quite a ways, doesn't it? Next slide, please. Well, I didn't have the plot I should have had. It depends on where you are on the moon. Some places the dust is 30 feet deep. Near the base of the mountains on the moon, it's 100 feet deep. There's a lot of dust there. And it doesn't turn out to be the kind of dust you might have thought. Now, this guy's putting up a collector target, and it collects the micrometeoritic influx, so we can see how fast the dust is really falling on the moon, and it turns out it's 1,000 times lower than was estimated. Now the question is, isn't this an argument that the dust is too deep instead of too shallow? Because the dust is there, and it isn't coming in, and the answer is, of course, while the solar system was forming, it was falling in a lot faster than it is now. This is all very old dust. Okay, last one. Earth's magnetic field decaying too rapidly. Okay, you picked it out because I don't have a slide for it, right? Dr. Russell Humphreys has done this one, and I think there's a Nobel Prize to be had, actually, if we do it right. Okay, it started with Thomas Barnes. 1979, I think, is when I first encountered his paper. I'll have to draw a graph here, X and Y. Strength of the magnetic field time here. We get kind of a decay, looks like an e to the minus x decay curve. What he's got is 100 years worth of data, measurements, and they squiggle around a little bit because, of course, data is never as clean as the people claim that report on it. But he draws this curve in and says, boy, the Earth would have been a magnetic star less than, we have to say 10,000 years ago or something. We always pick the same numbers for some reason. If it had really been decaying that fast. And you remember the trees keep a running tape recorder? This ocean's floor spread like this with a volcanic ridge going up between, and the lava gets laid down. Now, it turns out that the lava records the strength of the Earth's magnetic field on both sides going away from the mid-Atlantic ridge, and you can go back and see what it's done. Now, it didn't keep going higher and higher. It went up a little bit, reversed, went negative, came back, and did the cyclic thing, and the reverses are kind of random. So what was happening was not e to the x decay, it was something else. So Russ Humphreys comes along after the word's out that argument doesn't work and says, well, I'm going to come up with an argument that has reversals in it. And he does the same thing, and he goes through the kind of math that drives PhDs nuts because it's doing every trick that makes your head hurt when you do it. And he assumes that all the energy was in there to begin with and tries to do something with reversals. The only problem is it's pretty easy to show that there's an easier, or that you can get the magnetic field there and get it reversing another way. At the time he made the arguments, people were saying, we haven't figured out how to do it yet. There are good arguments that do it now, but I think there's still a Nobel Prize to be had, and I'm working on one. I hope to do it within the next 5 years. If I don't, I'm too senile and it won't ever happen. But if you won't promise not to tell anyone, I'll tell you how it works. Okay, here's the Earth here. There's a core. This thing is mantle outside, and inside is a liquid iron core. There's motion, the core relative to the mantle, and the core has the magnetic field lines in it, and when it moves, it drags the field lines through an intrinsic conducting mantle, which will generate currents in it. The same thing happens because these currents in the mantle will generate field lines that go into the core, which will generate currents in the core. And the two things play on each other. And it's actually on the web. I've got some plots of the history of the Earth's magnetic field for the last 100 years, and some plots of the currents of the core's fluid, and using the two and the map of the perpendicular field and those things, what it would generate, what kind of currents I would get. It appears to generate exactly the currents at the core mantle boundary that you see for the non-dipole components of the field, meaning that this system, without wasting any energy, generates the magnetic field. And I think I can prove the whole thing all the way through. If I can't, then I won't get my Nobel Prize, but maybe I will. I don't know. It's fun, but anyway, the point is, yes, at the time they didn't have an answer to it, but just because they didn't have an answer doesn't mean it's been proven that it can't be done. I think it can be done. I think I've done it. It's an interesting argument. I'm very fascinated by it and hoping to be the one that answers it instead of somebody else. Yeah, Mark?
I was interested in the Saturn's rings.
Oh, Saturn's rings, okay. Okay, there's a cool picture of Saturn taken from the back side. There's the dark side of Saturn. That's the whole dark side, and the rings kind of look eerie and glowy in some places where they're relatively young. How is this possible? Well, are they relatively young is the first thing. If the rings are as thin as some people claim, then they are relatively young. They would evaporate away too fast. They sublimate. You know about dry ice. It doesn't melt. It just boils away. And out in space, ice boils away. They're mostly dirty ice, just like comets. Just like comets. Don't think about that too much. Next slide. Well, there's a whole bunch of possibilities. Oh, you are thinking about comets. Sorry, it was my fault. Comet Shoemaker-Levy. Remember when it busted up back in the late 1990s? And smacked into Jupiter over and over again. Those are all little machine gun bullets. Each one of these things. Only a little piece of it whacked into Jupiter. Fortunately, it wasn't the whole comet. Not that it would have mattered, because I don't think Jupiter's inhabited. But in any case, this little thing here, that little spot, that's about the size of the Earth. If one of those had hit the Earth, it would have been bad news. Fortunately, it picked our neighbor. Okay, what happens if one of those comet pieces had hit another comet piece, or a moon, a small moon, and maybe the moon was a Kuiper belt object and shattered it? Well, or the comet piece, this got split up because it went inside the Roche limit of Jupiter. Actually, this was the second pass that it hit Jupiter. The first time by, it just got too close and gravity pulled it apart. Could have pulled it apart into a ring. Didn't this time. I was waiting when this was lined up to hit to see if Jupiter would get a ring. It didn't. Too bad, because it would have been a great argument, but that's not what happened this time. It would have had to have hit one of Jupiter's small moons, and it didn't. Next slide, please. Oh, sorry, back to 70. In any point, there was another slide I thought I had but never put on there. One of the arguments is maybe the ring is not made out of little pieces but big clumps, and there's a lot more ice there than we think, and it could have actually been there the whole time. I think probably not. I think it probably gets replaced on a regular basis. Now, it turns out all four of the outer planets have rings. Most of them are just very faint, and Saturn's is just amazing, probably because it's newly originated. And maybe if we wait long enough, we'll get to see a ring around one of the others. Probably not during our lifetimes. want to pick another argument. Yes, sir.
Well, this isn't up there, but AIG has this famous photo of a fossilized dinosaur footprint.
Paluxy River, Texas, Glenrose, right? Okay. Is it?
Page 111.
Oh, 111. Okay, we'll go for it. Sure. I'll get you some pictures here. This is called the Burdick footprint. Here's a picture of the Paluxy River with some supposedly human footprints and some dinosaur footprints going that way. And here's a footprint. Now that looks like a human footprint, right? Or at least a poor drawing of one. It doesn't look like a dinosaur to me anyway. Now it's way too big. It's 18 inches long, and there are a few other problems. But after all, there were giants in the land, so why don't we allow for it? You'll notice it's cut in a few places here because they wanted to see cross sections of it. And I wish I had the cross-sectional photos. I had them for one day. I did not take photos of them at the time. What the reason for looking at the cross-sections are is you can see the strata inside the mud. And you can tell by the way it swirls and stuff whether that was a depression from something like a heel squishing down or not. And the day I went to the Paluxy River was a Saturday night. Next Sunday, I, of course, go to church in Glenrose, Texas, and I don't remember whether it was a local Baptist church or whatever, but you always meet the one guy you need to meet for some reason. And he says, "Oh man, we've got that fossil in our it's in the bank security box, but I can't get to it till Monday." I said, "Oh, nuts! I have to leave before then." He says, "Oh, but I've got 8.5 by 11 glossies of it. You want to come over and see them?" And I said, "Oh, I'd love to." So anyway, he's got photographs of these cross sections there, and he says it proves that this is an authentic footprint. So I look at him and I look at the heel, and lo and behold, that's an authentic footprint. I can tell by looking at the mud that was something that squished and really made that impression. Next cross section I look at is this one here. And I look under the big toe. Man, that's an authentic depression. Then I look at toes 2 through 4. They were carved. Oh, nuts. Okay. I look at that and I say, okay, with a friend Steve, I push the photo over to him and say, okay, I go through the whole thing I just did with you. Look at the heel, look at the toe. See, it's authentic. So this guy from Glenrose is saying, yeah. And then I say, however, toes 2 through 4 are carved. The guy goes, no! And Steve says, I can see that. And I said, okay, you can argue if you want, or shove him his own photograph back. And he's just looking at that, and you can just tell he's nailed. Because he can see it same as anybody else can. This is not subject to your interpretation, your presuppositions, or anything. Those toes are carved, and you can tell. It doesn't look carved when you look at it this way. You look at the cross-section. The guys who took the photos didn't notice it. Their presuppositions may have been blinding them, but if they opened their eyes and looked, the evidence was there.
How many footprints were there?
There was only one of these. There were sequences that were claimed to be human footprints, like this one here, which turned out not to be. If you follow the tracks far enough, the whole foot comes down. The guy's running downhill. It's a theropod dinosaur, and he's only got his heel in the dirt. And when he gets to the bottom, all the toes come down, and you can see the whole thing. And you can follow it the whole way. There's no missing links or anything. These are all dinosaur footprints. There are no human footprints at the Paluxy River. You know that Answers in Genesis keeps a do not use list. All the really bad arguments, this is on the do not use list. A few more arguments need to be on the do not use list. In fact, all of them do. Maybe with time. Pick another one. They don't have to be scientific. They can be scriptural. You know, whatever you're interested in. I'll keep going until you get too hungry to listen. Yes, sir. Okay, that's a fascinating one. Do I have a number for it? I think I don't. No meter. Yeah, no number for it. Okay, my trip to the Green River Formation was really interesting. I'm looking at the strata a mile deep, and I get to this place where there are 4 layers. They're 4 inches apart about. 1, 2, 3, 4. There's actually a 5th layer in between the top 2, but there's something funny about it. And they're rusty layers. There's a bunch of rust, iron oxide. Now, we're out in the middle of this lake, and I follow this layer as far as I can, and the whole way it's still there. Whatever it was, somebody dumped a load of rust in this lake. You understand what I'm saying here? We're out in the middle of a lake that's 100 miles across, 10,000 square miles, and for some reason, somebody left a boat anchor that rusted away in the middle of this lake, and there's rust everywhere. Now, could I find a meteor? No. What are meteors made out of? They're made out of iron mostly. They're different kinds, iron, nickel, and iron rust. With a little bit of nickel in it, it won't rust right away. You leave it in the lake for 1 million years, it'll rust. And a lot of organic little critters are kind of iron deficient, and they'll gobble it up if they can find it and use it for making things like blood, except that some critters don't have red blood, but lobsters and the like use copper instead. Anyway, it's there, and you can actually find meteors. Every now and then you find one. I missed one. I could have got my name in the books if I'd been able to find a rock there. All I found was the crud left over from where four meteors hit in the same lake. Now, this is really interesting. We're going to start losing everybody. These were the same distance apart. Now, we've got to have some clockwork here that'll put layers 4 inches apart. If they're 1 millimeter, we're talking 25, about 100 years. 100 years later, same lake gets hit again. 100 years later, same lake gets hit again. 100 years later, same lake gets hit again. What is going on? What happens about every 100 years in astronomy? Halley's Comet, 70 years, right? Or something like that. Comets come around. What if we had a really fragmented comet? You remember that one that smacked Jupiter, hit it half a dozen times? What if we had one so spread out that every single time it came around, it got the Earth? The only way it could hit that same lake every time is if it nailed the whole Earth. Now, it turns out that this particular layer is a very good layer all over the Earth for producing huge craters. There's one in the Caribbean. There's another one in Chesapeake. You all know about the big Chesapeake crater. The whole bay has this huge crater in it. There are a half a dozen huge craters from just about the same strata as my Green River Formation rust. And what I think happened, and I'm still working on proving it, is that this was 4 hits from a comet, each leaving meteoritic debris. And I think it ties into the Moki Marbles, which were a different event that also left a series of horizons, a cometary sequence of geological column meteors. So A, there are meteors in the column. B, they rust away, so they're hard to find. And C, you can find a lot of things like tektites that are results of meteor that are very common, little glass beads from an impact that spews stuff all over the place. And D, I think I found some myself. So I can't prove that I did, but I think I will be able to eventually. It's an interesting field, though.
Yesterday at the church museum in the planetarium.
Yeah.
Was the spiral?
The spiraling galaxy. Let's go to that one. Where's that? Yeah, I remember that. That's 87 there. Okay. Here's a spiral galaxy. It's winding around. It turns faster in the center than it does on the outside, so it's going to wind itself up. Here's a very old galaxy. It's obviously lost all of its structure. Now, this is turning pretty fast. It ought to get to that quickly. How can there be any spiral galaxies left if this thing's been here 13.7 billion years? Wouldn't it have all got twisted up? Well, there can be new galaxies, but I'm going to allow for the moment that they were all created at the same time. I'll give it to them. Next slide. These are called the mice. These are 2 galaxies that got close to each other. They were obviously pretty old galaxies, and they're tearing each other up. Their gravity's pulling them out into some weird shape. They're going to go on past, and then they're going to have some really odd shape when they're done. And then it'll start twisting up again. Okay, next slide. And we'll get back to something like this. There's a force, or a system of forces actually, that you can watch happening that'll put it back into a spiral again. It's not a one-way trip. In fact, this will do things that'll start star formation. You can actually get star-forming areas where you got bright stars in something that would have been dead if it hadn't been disturbed by another galaxy. Okay?
Is that like the variant of like what they call the 3-body problem?
Well, it's worse than that. It's a 100 billion body part problem. But yeah, you can do it with a computer, but not so well with analytical methods. And in case anyone's wondering what this means, it's easy to do the math for one thing orbiting another, but if you have 3 bodies that are doing some orbit, you can't solve it analytically. You need to use a computer. That's called the 3-body problem, and you have to use a computer for anything with more than 3 bodies. And they break galaxies up into 1,000 elements and feed them through a computer, and they can actually figure out how they got into the shapes they're in. M51's a favorite one to study. It's a nearby galaxy that has a very interesting shape because of the interaction between two galaxies. All right, I'll be available for anything else.